Hi, this is Professor Dorr, and this is EE310 lecture number 7. In this lecture, I'll describe the relationship between complex exponentials and phasors used in AC circuits. We're going to demystify that dreaded e to the j omega t with intuitive arguments, counter-rotating vectors, and some simple math. So after you watch this lecture, complex numbers will be another tool in your toolbox, and phasors will just be a useful application of complex numbers. And you're going to be surprised how easy this really is. When I give this lecture in class, I have a captive audience, and I give them a long introduction, but I'll just give you the highlights here. If you open any textbook or any journal article, you'll see signals represented as e to the j omega t. It's common in textbooks and in articles to say the circuit is fed with complex exponential e to the j omega t. This frightens students and working engineers alike, and they just give up. And when they give up, that's when the learning stops, that's when the fun stops, and that's when careers stagnate. So I really struggled to learn this stuff, this relationship between complex numbers and phasors as an undergrad. And no professor could give me a good explanation. When I went and talked to the professor, this was a lot of years ago, the professor said, oh, well, you're supposed to know this in order to be in this class. Well, the truth is nobody ever taught this specifically. So it's almost like they were kicking the can down the road a little bit. So I left my undergraduate program confused about this stuff. So shortly after completing my BSEE, I attended a lecture by Fred Harris. He's a very famous professor at SDSU. I'll talk about him a bit later. And Fred explained complex numbers using many of the techniques in this lecture. And it was so clear that I never took a DSP course in graduate school. Then I went on to design digital radios and acoustic systems and control systems for the next 35 years in industry. Fred made it so clear that I just didn't see a need to take a DSP class. I just read some textbooks, but really I understood the fundamentals from this lecture. So if you're in my EE310 class, you're not going to be tested on this material. But your test is going to come as you continue with signal processing and later on in industry. If you master these fundamentals now, your career will be much more interesting, much more rewarding, and most importantly, even more fun. Before we begin this lecture, I'd like to dedicate this lecture to Fred Harris. He likes to have his name spelled with no capital letters. Fred taught this material with just tremendous enthusiasm and skill to multiple generations of SDSU students for over 50 years. I was one of those students in the 1980s, and Fred has remained a very good friend to this day. If you look Fred up on the internet, you'll see that there's a DSP window that's named after him. There's the Blackman window and the Hamming window, and there's also the Harris window. And that's a really cool accomplishment. But the accomplishment that so many of us in San Diego appreciate the most is just all the knowledge that Fred imparted on us. A lot of my teaching style has been just the best imitation I can of what Fred has done for all of us. So the motivation for this lecture is to reinforce your knowledge of complex exponentials so that you're going to thrive as a student, and more importantly, you're going to have the tools to continue learning throughout an exciting and interesting career. You may not fully grasp this lecture today, but it's my hope that you'll keep these notes and refer to them in the future. If you can't find your notes, or if you're viewing this lecture and you're not an SDSU student, send me an email and I'll get you a copy. So in a circuit, a sine wave is a voltage or is a current. It's not a complex or imaginary number. There are no imaginary numbers rattling around in circuits. The term imaginary number, to me, is just misleading. The reality, though, is that complex numbers, which have imaginary parts, are commonly used for AC circuit analysis. So in EE310, complex exponentials are used for AC steady-state circuits. In your senior level coursework and when you work in industry, you will use complex exponentials to describe circuits, analog and digital filters, control systems, communication signals, and you're going to find that modern signal processing is built on a foundation of complex exponentials. People came up with this stuff a long time ago. Smart people have thought about it for a long time, and nobody's figured out a better way. I like roadmaps to see where we are. So I drew this little roadmap because I kind of wanted to put today's lecture in perspective for you. So you're learning about signal processing. That's you following that little arrow down there. And you started off learning about DC circuits, and then you got into EE310, which is the class that this lecture is a part of. And we start off with second order time domain circuits, RLC circuits. I like to call it thuds and boings because you have overdamped circuits that thud, and you have underdamped circuits that go boing. So we start off the course, and where we are right now is we've just done several weeks of these second order time domain circuits. But now we're going to take a big step, and we're going to move towards sinusoidal steady state analysis. And then after we do this, and frequency response will be in here, we're going to do thuds, boings, and sinusoidal analysis using the Laplace transform. So what you'll see is that we're going to learn some cool specialized techniques back here with the second order circuits. And to me, the real value is that you learn how to look at circuits and just figure out intuitively what they do and then apply the math to them. But when we get up into Laplace transforms, we're going to generalize everything so that you can do both sinusoidal and transient analysis. And you see, this is the boundary of EE310. But you're going to pass this class, and you're going to get out of EE310, and you're going to do digital signal processing. You're going to do complex communication waveforms. And then you're going to have an awesome career when you leave SDSU, and you're going to make me proud and come back and buy me a cup of coffee. But in this timeline, what I've seen in 35 years in industry and as a professor is that complex exponentials are the gap in most engineers' understanding. Because you're hanging on by your fingernails trying to get through EE310, and you're happy just learning that the impedance of an inductor is J omega L and the impedance of a capacitor is 1 over J omega C. That gets you through the final. And I get that. I understand that. But what happens is I interviewed a lot of engineers when I have my company and afterwards, and complex exponentials are the gap in engineers' understanding. And so what I want to do is, right as we introduce AC circuit analysis, I want to give you a background in complex exponentials so that you'll see that AC circuit analysis are just kind of an application of this tool, which is going to be a tool in your toolbox. So here's where we're going. We're in EE310 now. Hopefully some people watching this lecture are way out here wishing they remembered this stuff. And I'm glad that you're watching this lecture, and I hope it helps you. So the motivation, circuits before 1900. Engineers, physicists, and mathematicians, they knew that when a sine wave was fed to a circuit, the output at the voltage or current at any point in the circuit was also a sine wave, but it was scaled in amplitude and it was shifted in phase. And the amplitude scaling, well, we could handle that with a simple multiplicative constant, but the phase complicated things. So also back then in the olden days, the differential equations describing inductors and capacitors, namely V sub L equals L di dt and I sub C equals C dV dt, they knew those. But differential equations had to be solved every time you analyzed a circuit. So General Electric had to electrify an entire country, and the linemen and technicians and engineers in the field couldn't always solve differential equations. So they need a better analysis technique. And the person who did that was George Steinmetz. And in our textbook, there's this great picture. It's a real old picture because it was a long time ago. George Steinmetz sitting there pumping on a stogie. It's a great picture, actually worth looking up. Our textbook, Alexander and Sadako, is just an excellent book, and it's full of all kinds of good technical information, plus just good background information on the field. They did a beautiful job with that. So what we're going to use is the Euler Identities. And you've probably seen these before, but let's present them again so we have them all in one place. So simply, the Euler Identities say e to the j phi, where j is our complex operator. The mathematicians use I as the complex operator, but in electrical engineering, we use I for current, so we use J. But here's the basic formula for the Euler identity. E to the j phi equals cosine phi plus j sine phi. In other words, it's a complex number. And in high school, you dealt with complex numbers, you put them on the complex plane, and you put the real part on the real axis, which was your x-axis, and you put the imaginary part on your y-axis, and you did a whole lot of graphing, and everything sat still. Well, we're going to do that graphing in this lecture, but now it's going to be vectors, and they're going to be whirling around. So let's take our basic equation here, and let's solve it for the cosine or the sine. So the cosine is equal to e to the j phi plus e to the minus j phi divided by 2. And the sine is equal to e to the j phi minus e to the minus j phi divided by 2j. So these are the Euler identities, and we're about to get our money's worth out of them. So when referring to how signals are affected by circuits at a specific frequency, or in other words, we got a circuit, we put a signal into it, and we want to see how the circuit affects the signal, phi will be a constant. For example, a signal can be shifted in phase by phi radians by multiplying it by e to the j phi. And when referring to time-varying signals using complex number, phi is actually going to be a phase angle that increases linearly with time. So phi is actually going to this phi here is going to be phi of t, and this is going to be phi of t. So that phase angle is going to change linearly with time. So if I represent that, I'll take my cosine and I'll replace phi with I'll replace phi with omega t. So phi is a phase angle that increases linearly with time. So let's consider a cosine signal using the representation of this equation right here. We know that it is a, some amplitude, times the cosine of omega t plus, let's say, phi 1. We're all used to seeing equations like this. It's a cosine with an angular frequency omega, and it has some constant phase shift phi 1. So I'm going to use the Euler identity, and first I'm going to multiply my signal by a, that's right here, but then I'm going to replace that cosine with the Euler identity. And my phi, which we called omega t down here, and now I'm going to generalize it even more and say it's omega t plus this constant phase, is shown right here. So this is an equation, but it's got a lot of stuff going on. So what let's do is let's make it simple and intuitive. So the right-hand side of this equation can be represented by two vectors. And the upper vector is going to have a positive frequency and rotate counterclockwise, and the lower vector has a negative frequency and rotates counterclockwise. And you'll see that when these vectors are added, the imaginary parts cancel, leaving a signal that moves back and forth on the real axis. And the phase angle, the constant phase angle, that phi 1, causes a constant phase shift. Let's look at it. So these two vectors are these two components. The first vector, moving counterclockwise, is e to the j omega t plus phi 1. Here it is. And I'm sorry, it's e to the j omega t plus phi 1 divided by 2. And here's that vector. And as t increases, of course, it rotates around because the amplitude doesn't change, but the phase changes. So the first vector in that expression is moving around counterclockwise. Now let's look at the second term. And here we have the same thing here, j omega t plus phi 1, but now we see a negative sign. So this term, of course, it has the same amplitude, a over 2, but it is rotating clockwise. Let's look at this term now. Here's that second term. So what our equation is showing us is that I have one term whirling around this way and I have one term whirling around this way. But what you can see here is that the imaginary parts cancel at any time. See that? This vector has a real part and an imaginary part. This vector has the same real part, but the negative imaginary part. So the imaginary parts will always cancel. So when I look at the result of adding these are both a over 2, so they're going to add to be, they're going to add up to be a, right? But as these vectors are going around like that and the imaginary parts are canceling, the result is just on the real axis. So here we go. These two are flying around and the phase angle is changing linearly with time. And the result of adding them is just going back and forth on the real axis. And here it is. And at time equals 0, when time is equal to 0, this vector was at angle phi1, and this vector was at angle negative phi1. So that means that, here's my phi1, this is showing time equals 0. Well, check it out, look at that. We just accounted for the phase shift in that cosine. So let's back up. We started off with a cosine. We turned it into two complex counter-rotating vectors, and then we showed what they look like, and then we added them up, and we said, duh, of course, the result is going to be real, but we could see that it's real because these imaginary parts canceled out. So what the verbiage describing what we just did is right here. So read that through again, and in your mind, make these vectors counter-rotate, and you can just see that imaginary part canceling out. So what you might be wondering here, and it's a good thing to wonder about, but you got to stick with me, is why did you take something simple like a cosine and make it complicated and then say, hey, look at this, it turns into a cosine at the end? And the reason for that is that since these are moving with a counter rotation and the imaginary part cancels out, we can just work with one of them at a time. But we're going to get there in a bit. So the phase of my cosine that I showed up here, if I want, I can shift it by some constant phase angle. So I'm just going to do a phase shift, a constant phase shift. And the way I'm going to represent that is down here. A cosine omega t plus phi1 plus phi2. So I'm adding a phase shift. And I put it in here. And here's my phi1 plus phi2, phi1 plus phi2. What does this do? It multiplies the upper vector, or in other words, this one, by e to the j phi2, and it moves this vector by e to the minus j phi2. So it's going to basically kick this vector over this way a little bit. It's going to kick this one over this way a little bit. Let's look at a picture of that. What I'm doing is I started off with phi1. That was when I had just a cosine omega t plus phi1 by itself. But now at time equals equals 0, I want the phase angle to be phi1 plus phi2. So I'm going to rotate this one phi2, and I'm going to rotate this one phi2 the other way. My total angle, of course, is phi1 plus phi2. So you might say, well, why are you going to do that? And the reason where I'm going with this is what circuits do at a fixed frequency is they add a phase shift, and they also scale, but they add a phase shift. So this is kind of an introduction to what circuits are going to do to our exponential signals. And so you see that the upper vectors in the two figures rotate counterclockwise and therefore have positive frequency. And the lower vectors rotate clockwise, and we say they have negative frequency. And in the next section, we're going to show that when a sine wave is fed to a circuit, the circuit scales its magnitude and shifts its phase. when signals are represented as shown in figure 2 and figure 3, the circuit will shift the positive frequency component by a constant phase angle and the negative frequency by the negative of the same phase angle. And we also note that the amplitude scaling is an even function of frequency, and the phase shifting is an odd function of frequency. And that ensures that the output of a circuit when fed with a real signal will always be a real signal. There's no such thing as imaginary signals rattling around in circuits. So again, what that just said is that say we put in a sine wave into a circuit and it's got some phase offset to it, but now we're going to go through the circuit, and what you're going to see is that at a fixed frequency, when I look at the output, when this sine wave was fed into the circuit, I'm going to see a phase shift, and then you're also going to see a shift in the amplitude. Now that we've got some of the basics in place, let's look at how we analyze circuits using complex numbers. So what I'm going to do is I'm going to just go straight down to the graphic here. And here's what we're going to do. We're going to take a signal, this Vn equals A cosine omega t plus phi, which looks like this. And we're going to put it through this circuit, and this circuit has inductors and capacitors and resistors and stuff like that, linear elements in it. And the output of the circuit is going to be a scaled in amplitude but shifted in frequency sine wave at the exact same frequency that went in. That's a property of linear circuits. If I put a sine wave into the circuit, then the output resulting from that sine wave at any point in the circuit will have the same frequency, meaning that it'll have the same frequency and its amplitude will be scaled. So what the filter does is amplitude scaling and phase shifting. So it's usually we have the input of our circuit on the left, the output on the right. But to make my graphic easier, I made it so that we're going to put the input in the top and the output is going to come out the bottom. And you can see it has that same frequency, but it's just a little bigger in this case. So this is going to show the operations we're actually going to do on the signal graphically. So we have Vn equals A cosine omega t plus phi. Let's use Euler's identity and break that up into a complex number. And we do that and we get our two counter-rotating vectors. This one is rotating this way and this one is rotating this way. And of course the imaginary parts are canceling because after all it is a cosine. And there's no imaginary part in a cosine. So we just made things a little more complicated. So here is our input represented as a complex exponential. So now let's look at what the circuit does. This graphic is showing just the circuit. So I'm saying it's the circuit represented as a complex exponential constant, because at a fixed frequency, that's what the circuit does. It is a complex constant. And so what the circuit is doing is it's shifting the positive frequency components by this angle gamma and scaling them by the magnitude of this vector. And it is shifting the negative frequency components by negative gamma, and it is also scaling them by the same constant. So this vector is just representing what the circuit does at a specific frequency. these aren't whirling around, but you notice the imaginary parts do cancel, of course. So I'm going to take this signal and I'm going to pass it through this filter. And what that is going to do is, one thing I forgot to mention is that the amplitude scaling that the filter does, we're going to represent with just the absolute value of h. So let's look at what our output is going to look like. We're going to shift by gamma, and we're going to scale by the magnitude of h. And so my result over on this side is going to be A, which was our initial amplitude, times magnitude of h, times e to the j omega t plus phi plus gamma, or in other words, it moved our vector here at phi up by gamma, and it moved this one at minus phi by gamma also. And here is the complex representation of what comes out. Now let's use Euler's identity and turn it back into a cosine. And it's just A times h cosine omega t plus phi plus gamma. Or in other words, what the circuit did is it scaled our input by h, and it shifted the phase of our input by gamma. And here is our resulting signal. So in the last example, it kind of looked like I was taking something simple and making it a little more difficult than it needed to be. But now I'm going to show you how we can streamline the process, and we're starting to move toward the efficiency of the phasor approach. So this figure over here shows that how we can actually streamline the steps. So first, we notice that for any real signal, and all the signals we deal with are real, there are always two counter-rotating conjugate vectors, meaning you always have a vector going this way, and there's another one going this way. And second, we note that the circuit scales the amplitude of the two vectors by the same amount, and it shifts the input vectors by conjugate phase angles. So our strategy is we're going to do our calculations on the upper vector only. The way I like to think of it is for a cosine, I've got a sinusoidal signal, I've got these two counter-rotating vectors. But I like to think that the lower vector is just kind of following the upper vector like a little dog, right? The upper vector goes that way, the lower vector is going to go that way. So if I know what the upper vector is, I know what the lower vector is going to do. And for the circuit, here's our circuit, same kind of thing. It's going to shift the positive frequency components by this amount and it's going to shift them by gamma phase, and it's going to scale the amplitude. And I know that it's going to be conjugate for the negative frequency components. So in other words, if I know what's going on here, I know what's going on here. So our strategy is to perform the calculations on the upper vector only. So you'll see that this figure looks a lot like the last figure, but I just have the upper vector. So as before, the input to the circuit is going to be our A cosine omega t plus phi, and we're going to represent that with as a complex number, and it's going to have counter-rotating vectors. And what I'm going to do is I'm going to just chop off the lower vector, because if I know what the upper vector's doing, I know what the lower vector's doing. So here's our chop. We pulled out this negative frequency term, And now we just have A over 2 e to the j omega t plus phi. And here it is right here. We just have the positive, the rotating vector. Now the circuit is going to scale the magnitude of our input vector by a constant h, and I kind of show that over here, and it shifts it by a phase angle of gamma. In other words, it's going to scale this thing in amplitude, and it's going to go whoosh, and it's going to shift it by gamma, and here is the output of the circuit. Again, this is a complex constant. This is what the circuit does at this frequency. Here is my input signal that has been shifted by gamma, by the phase that the circuit will cause, and it's scaled. So the result is going to be my initial amplitude scaled by h and phase shifted. And that's shown right here. So what I'm going to do now is I'm going to say, well, I know that the upper vector is here, so that means I know the lower vector is following it like a little dog, so it's going to be down here. So let's just restore it. Or in other words, I have my expression for the upper vector. Let's just put the lower vector back in. Here it is. And now I use Euler's identity, and I have my answer. Okay, so now let's look at circuit relationships for sinusoidal signals. So in the previous section, we found that complex exponentials can be used to manipulate magnitude scaling and phase shift caused by circuits. And we found then that we could streamline this process by using a complex exponential instead of a cosine or sine. Now, what I really mean by that, in this representation, I'm not feeding the circuit with a cosine. I'm feeding it with a complex exponential of a over 2 e to the j omega ct or j omega t plus phi. And this is the basis for why in journal articles and textbooks they say we're going to feed the circuit with a complex exponential. It's because they're just giving us the upper vector and not the lower vector, because the lower vector is going to follow the upper vector like a little counter-rotating dog. So we found that we could streamline the process by doing that, just feeding the circuit with a complex exponential instead of a cosine or a sine. Now, the circuit blocks in figure 4 and figure 5, namely our little circuit here, these blocks are going to be replaced by actual components. And the analysis is simplified because the function e to the j omega t has this wonderful property that its derivative with respect to time is simply j omega e to the j omega t, right? I take the derivative of this complex exponential with respect to time, and j omega, that's constant, so it just goes out here. So I have j omega e to the j omega t for my derivative. So if the current through an inductor, I sub L, is equal to e to the j omega t, then the voltage across the inductor, well, we know that's going to be V sub L of t is equal to L di dt. Well, let's just use our formula. Di dt, we know I is e to the j omega t. Let's take di dt. So that means we just put a j omega out in front of it, like this. So V equals L di dt equals L times j omega e to the j omega t equals j omega L times I. And we can solve for the inductor impedance. V sub L divided by I sub L is Z sub L equals J omega L. Hey, you already knew that, but this is where it came from. The idea for this, where this comes from, is feeding circuits with complex exponentials, because that's what we did. We said that the current is a complex exponential, so we could get its derivative and we could throw it into our wonderful equation for the inductor, and we ended up with J omega L as the impedance. Now similarly, the voltage across the capacitor, if the voltage across the capacitor is Vc of t equals e to the j omega t, the current through the capacitor is going to be I equals C dV dt, and same trick. Take the derivative of this e to the j omega t, and C dV dt becomes C times j omega times e to the j omega t equals j omega c Vc of t. And the impedance of the capacitor is Vc divided by IC is equal to the impedance, and it's 1 over j omega c, another formula that you are already familiar with. Again, where do these formulas come from? They come from feeding circuits with complex exponentials. So, if the voltages and currents in circuits have the form e to the j omega t, the inductor impedance can be expressed as j omega L, and the capacitor impedance is 1 over j omega c. It's an algebraic relationship, not a differential one. And boy, were those linemen out in the field who were electrifying the country glad to see that. They could work with algebra instead of calculus. And this is what enabled them to do their calculations out in the field. And this has worked for 100 years. Now, if the input to a circuit is Vn of t equals e to the j omega t, then the voltage and current signals S at any point in the circuit. You got a circuit, just throw a dart at it, any point. Sn of t, or the signal at whatever that node is of t, is equal to the amplitude at that node times e to the j omega t times e to the j phi of n. Or in other words, here is our input, e to the j omega t. It gets scaled by an amplitude that's associated with whatever node our dart landed on, and a phase shift, which is the phase shift at that node where our dart landed. Of course, the phase shift, you notice, is a constant. The signal is that rotating vector. We know it's got a counter-rotating vector, but we're just dealing with the positive vector. So here's our signal, and you can see the phase angle incrementing with time. Here's our phase shift at a specific frequency. It's a constant. So here is the result we get. Okay, so in other words, the effect of the circuit at any node is to multiply the complex input by the complex number a sub n e to the j phi sub n. And the ratio between the circuit output and input signals is called the transfer function, or h of j omega. H is a common term for transfer functions. And we say that the transfer function is actually a function of frequency. Why is that? Because at different frequencies, this phase and this amplitude are going to change if we change the frequency. That's why I say this is constant at a specific frequency. Now, in our next unit, we're actually going to look at how circuits characteristics change at different frequencies, but we're not there yet. So let's do an example. We're going to do a circuit excited by a sinusoidal signal. So Vn of t is equal to 3 times the cosine of 2 pi times 3000 t. So here's our input. Looks like we have a 4.7K resistor, and then we have a 0.01 microfarad capacitor, and here's our output. So we want to find the output voltage. So what we're going to do is we're going to remove the negative frequency vector from the input, and using omega is equal to 2 pi times 3000, right? 2 pi times the frequency in hertz. We're going to use this for the angular frequency, and we're going to say that the circuit we're feeding in to this circuit is 1/2, whoops, because remember we had the two vectors, and that's where that 1/2 creeps in, times 3 times e to the j 2 pi 3000 t, and we have 3/2 e to the j omega t. So what we're doing here is what those textbooks and what those journal articles do, and we are just shoving a complex exponential into our circuit, just like the smart people do, but it's really not all that hard. So the strategy is to compute the complex transfer function of my circuit, which is V out divided by V in. And then we're going to compute V out by saying V out is equal to the transfer function, V out over V in, times V in, which is just going to be H of omega, or I'm sorry, H of omega times V in. That's going to give us V out. So here's our input signal represented as a complex exponential, and it's feeding our circuit, and we're going to get the transfer function of our circuit using voltage division. Or in other words, H is equal to just the impedance of the capacitor divided by the impedance of the capacitor plus the impedance of the resistor. It's just a voltage divider. So ZR and ZC are the impedances, the resistor and capacitors, respectively. And the impedance of the resistor, of course, is just its resistance. But the impedance of the capacitor is computed using equation 16. It's just 1 over j omega c. So our transfer function, ZC over ZC plus ZR, is going to be just 1 over j omega c divided by R plus 1 over j omega c, and we multiply top and bottom by j omega c. We get 1 over j omega RC plus 1. So now let's evaluate that transfer function at 3000 hertz. And remember what this is going to be. Remember we said what the circuit does is a constant at a specific frequency. So we're going to put in our 3000 hertz and we're going to get a constant. And we do all our complex math here, and we end up with 0.5603 minus j 0.4964. Let's look at H on our previous pictures. Here's H right here. Here is that complex constant. It has a real part, it has an imaginary part. It's constant at a specific frequency, and we just calculated it. And it is our what the circuit does. Here it is. So the positive frequency term of the output signal is just going to be V in times H. And you notice I didn't say H of omega here because we calculated our H as a constant because we evaluated it at 3000 hertz. So it's going to be 3/2 times my input, e to the j 2 pi 3000t, multiplied by, and here I changed our circuit to a polar form, so times 0.7485 at this phase angle, and here is my output. So I put a complex input in, I got a complex output out, but I know what I really get is cosine out. So let's just restore that lower vector. If the negative frequency vector at the input had not been removed, the output would consist of the signal of equation 25 plus its complex conjugate. Let's put it in. Here we go. And from our equation 4, or just our Euler identity, we can pull the output voltage, and here it is. And you can see that the output is a scaled and phase-shifted replica of the input. So what we did is we're still doing it the hard way, though we have pulled out that lower vector. But in the last example here, we just did it for a circuit. Now what let's do is let's jump full bore into the Phasor method. So the previous example showed that a sinusoidal input could be represented as a complex exponential and then used as the input to the circuit, like the smart people do who write the technical articles in textbooks. And the complex input can then be multiplied by the circuit's transfer function, resulting in the complex exponential representing the circuit output. Now we're going to adopt the familiar phasor notation. Since the frequency is the same for any signal in the circuit, phasor notation retains only the magnitude and phase angle, right? A phasor just has a magnitude and a phase angle because the frequency of all the signals in the circuit will be the same as the input. So we draw our little line for phasor relationships, which now you understand this. You can do this from first principles pretty easily, but we're going to streamline things and show our little equivalent symbol here. So if we have V max, which is a peakier cosine, right? V max cosine omega t plus phi in radians, we represent that with a boldface V equals V max times at an angle of phase in degrees. Kind of strange, phasors use angles in degrees, get used to it. And it was shown that a transfer function at a single frequency is simply a constant scaling constant, a complex scaling constant. So for example, in the previous example, the transfer function was the complex ratio of the output voltage to the input voltage. And so we calculated our transfer function. And in the previous example, the phasor representation of our input voltage is going to be just 3 volts at an angle of 0. And the phasor representation of the transfer function, V out over V in, is just its magnitude and its phase. Or we can show it like this, 0.7485 at an angle of minus 41.5 degrees. Or if we want, we can call it 0.7485 e to the minus j 0.725. This is probably what you're more familiar with. So now we have a phasor representation of our input. We have a phasor representation of our circuit. And the output of the circuit is just found by multiplying the input by the transfer function, just like we did in the last example. Since this involves multiplying exponentials, we multiply the phasor magnitudes and we add the phases to get the answer. So now we're in phasor land. Boldface V out equals boldface V in times boldface H is equal to 3 at an angle 0 times 0.7485 at an angle of minus 41.5. Multiply the magnitudes, we get 2.25. Add the phases, we get minus 41.5. And since V out is a phasor, we convert it to a sinusoid by inspection using our equation 28, which had our little equivalence relationship. We got a Vmax at a phase angle. Here it is. Vmax at a phase angle, and our equivalence just tells us that that is going to be cosine omega t plus phi times Vmax. Here is our answer with no complex numbers. So, the good news is that we can solve steady-state circuit problems with algebra and complex numbers. We don't have to use differential equations each time. In the next several lectures, the Phasor method will be introduced in more detail. And these phasors have been used for 100 years. Nobody's figured out a better way. But here's the bad news. The Phasor method is so streamlined, and we'll use it so much that it's easy to lose sight of where it came from. And if you lose sight of where it came from, you get through EE310 and you can probably get through EE410, but you won't have that nice grounding in signal processing. With this gap, if you leave this gap here, you can still get through EE310. But if you close this gap, EE310 will be this wonderful springboard for all of signal processing and the rest of your career. In my career, it's been a long one, but the technologies have always shifted underneath me. But by understanding the fundamentals really well, all I had to do is just buy a book and read on whatever the latest thing was, whether it was microwave radio or cellular radio or control signals or avionics or, cellular, all the different things I've done in my career. Because I had a really good knowledge of the fundamentals, I could always shift from technology to technology. And I had a tremendous amount of fun doing that. And I guess my ultimate non-financial reward is being able to share all these fundamentals, not only the fundamentals themselves, but also the enthusiasm for them with you. But the Phasor method is so streamlined, it's easy to forget where it came from. So the future, you're going to encounter complex exponentials in your upper division courses, and your instructors are going to expect that you have a working knowledge of them. When you get out of school, you're going to need to learn a new technology because the technology will have shifted underneath you after you've been out for 10 years. And you don't want to go sell real estate at that point. You want to keep being a good engineer. So if you know these fundamentals real well, you're just going to move with the technology and just keep having fun. So the bottom line is that complex exponentials are nothing more than what was presented in this lecture. If you're ever intimidated by complex exponentials, just refer to this lecture. If you can't find the lecture, or if you're watching this on YouTube and you're not in my class, hit me with an email and I'll be happy to send you a copy.